Okay, turbulent modeling basically is a very special topic in computational fluid dynamics, and this is very important because computational fluid dynamics is all about modeling technique, and turbulent flow actually, or turbulent physics is actually a very complex in nature. So that's why turbulent modeling is always, have become a very special topic, and the development is always going until now. And first, to appreciate how important is turbulent modeling, we must understand first about the turbulent itself. So turbulent basically is like a flow that consists of high, unpredictable random motion, transient, three-dimensional, and have a huge scale. That's the most important thing that you have to understand. Let's say we have a building with, let's say 15 meter in height. The flow around it created a turbulent flow that maybe makes a swirling motion, or we call that eddy, with the size of about a couple of meters. So it's almost the same size as the building. But the eddy itself creates a very random motion which dissipates and make smaller eddies, which can be in the scale of a couple of millimeters. So you know that we have a large range of scale, and smaller eddy sometimes swirling faster compared to the large eddy. So let's say we have a large eddy, the motion will be, let's say, need a couple of seconds to rotate, but for small eddy maybe just like a millisecond to create a single rotation. So beside the scale different, we also dealing with the time scale, which is very hard to handle with the computational fluid dynamics. So imagine if you want to simulate the whole simulation, or the fully resolve the turbulent flow, you must make a mesh that this large or this small, like a couple of millimeters, to cover all of the, let's say, 15 millimeter building. So and also the time step, you have to set it like a make milliseconds. So the computational effort will be excessively large. And again, that will not be feasible if we are doing the fluid dynamics, or computational fluid dynamics. So the best way to accommodate that scale, or maybe that complex phenomenon like the randomness, which is will be impossibly solved using the analytical solution from the Navier-Stokes equation. The best way to do that is by model, make a model by using some simplified technique. But first, before go there, I will also show to you that in computational fluid dynamics we also have the direct numerical simulation, which is solving the Navier-Stokes equation with discretization, of course, but fully resolve the turbulent scale. So you can expect a very, very fine mesh, and also very, very small time scale. So the simulation will fully resolve the turbulent scale. And in fact, OpenFOAM also has this direct numerical simulation solver, but it is only feasible if you are having a very high, a very high performance computer. Let's say if you are working in NASA, let's say, or maybe in some largest university in the world that has this computer or supercomputer. But for daily engineering application, it will not be feasible. So we will not talk about this direct numerical simulation, except you are very advanced and want to prove some basic theories like turbulent flow, or complex mixing interaction, let's say, or the complex reaction flow or combustion. prove some basic theory, maybe you will need this direct numerical simulation. But if you are engineer working in a company to solve some certain design problem, that will be not necessary using this direct numerical simulation. Then we also have the large eddy simulations, which models the turbulent by its eddy size. Let's say if we have this, like 1 meter length of flow and has certain amount of eddies with some certain millimeter of diameter, the large eddy simulation will solve that specific diameter of eddies. So you don't have, or the computer don't have to solve its simulation or its eddy size. And this is quite useful to solve this large flow. For example, if a flow like a plum of a smooth like this, or maybe if we are simulating a flow around a building to see the effect of the detailed transient flow, it will be feasible. But because we only resolve some certain scale of eddies, for some smaller eddies, let's say near the wall, maybe that we are simulating let's say we are simulating an airfoil with the flow eddies as in the wake region, it has like a couple of centimeters of eddy size, but we must know that nearby the wall, which is the no slip condition, we will have like a couple of millimeter or even like a micrometer of eddies that again that will not be fully resolved by the large eddy simulation. So the problem with the large eddy simulation is the flow nearby the wall. So because the idea is if the flow comes near to the wall, the eddy size or diameter will be smaller and cannot be solved by the filter of the large eddy simulation. Then maybe the most common turbulent model used in the industry is the Reynolds average Navier-Stokes. So the basic idea is to just basically make the average values of the parameters like velocity, pressure, and maybe temperature, etc. So instead of solving its eddies, it just like basically averaging the whole flow. The whole eddies become average velocity like this. So for example, if we have like a eddy flow like this, very complex back and forth motion, the filter of the Reynolds average Navier-Stokes is just to make it like like a bulk velocity. So if we have a fluctuation velocity like this, the Navier-Stokes equation just make it averaging it. So it will be very feasible for in terms of the computational effort. Let's say if we have even for large eddy or smaller eddy, or even smallest in nearby vicinity of the wall, it will be no problem to be solved with the RAS, because like it doesn't matter you have a small mesh or large mesh, it will be the same, can be solved easily by just averaging it everywhere. But the problem with this RAS is because we just using the average value, we cannot get the fully detailed of like a fluctuation term. And if we see this picture, we compare the RAS and LAS side by side, we can see that we lost of like the detail of the flow itself. So if you want to see the detailed interaction, let's say for the transient flow, we only get this kind of picture that we cannot explain everything with this, of course. But if you just want to solve, for example, the drag coefficient or lift coefficient, or maybe the temperature distribution of a building without really need to understand the detail of it, RAS will be very sufficiently solve that. And again, computational fluid dynamics is all about the modeling technique. So it highly depends on your application. If you want to solve like like to compare two model of a racing car, let's say, or maybe like you have a 10 of models, you cannot solve it by the less. Of course you can, but it will be not computationally feasible in terms of the time and the computer effort. So sometimes runs is become the most feasible if you like like have lots of variations, like maybe hundreds of geometry. You want to just compare which are the best. But once you want to know the detail of the flow, the less will be beneficial. But the problem again with less is if you have a flow nearby the wall, it will be problematic. So we also have other option, which is the hybrid RAS and less. And the basic idea is basically just using the less everywhere in the free stream flow, but for the flow near the wall we use the runs instead. So it will be basically solve the flow nearby the wall, or like for the smaller eddies, but you will not solve the eddy itself, like make the calculation of the average value nearby the wall, and you will solve the whole flow or the flow far away from the wall by the less. So it will be like a good combination between RAS and less, but again it will not be as fast as RAS and not as detailed as less. So always a trade-off in the turbulent modeling. And maybe this is just the general map of the turbulent models. You see that the RAS is in the bottom of this accuracy and fidelity. Fidelity means like how realistic the flow will be. It is called the fidelity, or like the quality of the graphic. And the accuracy is about the values, or the like a fluctuating terms. And higher the accuracy and fidelity, it will has higher computational effort. So you can see this general map. Of course, it is just like a general map. So like it is always like situationally different. Let's say if we have a RAS, but we have a very detailed mesh, of course the effort will be higher compared to less if we use like non-proper mesh. But generally, if we use the proper simulation technique, the map will be like this.